What if we could build a computer so powerful that it could help discover new antibiotics, solve the conundrum of nuclear fusion, or even break today's encryption algorithms? Quantum computing promises all this and more by harnessing the quirky properties of particle physics. But to achieve big scientific breakthroughs, quantum computers will need to perform better than today's best classical supercomputers at solving real-world problems, what's called quantum supremacy. So what is still holding quantum computing back from becoming actually useful? In this episode, we find out what problems researchers are still wrestling with and how close they are to overcoming them. I'm Gemma Ware, and this is The Conversation Weekly, the world explained by experts. Hi, Eric.
Hi, Gemma.
Good to have you on the podcast.
Thanks for having me.
So Eric Smalley, you're the science and technology editor at The Conversation in the US, based in Boston. And I'm hoping that you know a thing or two about quantum computers and can help give us some context.
Yeah, I've been tracking quantum computing for decades now.
Okay, so I'm going to put a few questions to you in the simplest way you can. What is a quantum computer and how different is it to the ones that you and I are using right now to talk to each other?
Right. So quantum computers use quantum mechanics, the laws of physics that govern the behavior of atoms and subatomic particles like electrons and photons to solve mathematical problems, to essentially compute. At the quantum scale, things get fuzzy and kind of counterintuitive, more a matter of probabilities. For example, a particle can exist in a mix of multiple states at one time. It's kind of hard to get our minds around how that works because it's so different from our everyday reality. But scientists have figured out how to use quantum mechanics to calculate a whole range of possible answers to a problem all at the same time.
And why are scientists doing this? And why are, companies like IBM and Google, the big tech companies, really putting a lot of money into this quantum capability of computers?
Yeah, quantum computers have the potential to solve some problems that are actually beyond the reach of the most powerful supercomputers, problems that have huge numbers of variables that are just really difficult for ordinary computers to do. In some cases, there are types of problems that the most powerful supercomputer in existence couldn't solve if it was given the whole lifetime of the universe to try it. The catch is that quantum computers don't necessarily solve all of these types of problems, but it does look like they can be good for certain problems. Some of them are quantum simulations, so modeling what's happening at the quantum scale. And this is important because it can be helpful for things like developing new drugs or developing new materials. They might also be good for combinatorial optimization problems. This is a class of problems where you have a whole range of possible solutions and you want to try to figure out what's the best of those. The classic example is the traveling salesman problem. How do you find the most efficient route through a whole bunch of destinations? But this is useful for more than just planning routes. For example, the most efficient layout for circuits on a computer chip. And there's even some indication that quantum computing might be helpful with AI.
Okay, so some really big potential use cases, but it's not ever going to be something that you or I have in our household. This is really kind of scientists and people in big research labs who are mainly going to be using this. Is that right?
Right. I mean, you can think of it as kind of like a kind of a supercomputer or a very specialized kind of a supercomputer. So yeah, you're not going to have a quantum processor you can slip into your computer or that comes with your laptop.
And this past December, Google announced that it had made a big breakthrough with the launch of a new quantum chip that it's called Willow.
Introducing our latest quantum computing chip, developed to learn and evolve like the natural world around us. Willow, from Google Quantum AI.
Why is this announcement from Google such a big moment, Eric?
One of the main hurdles to building quantum computers is that they're quite error-prone. This is due to the same laws of quantum mechanics that give them their power. And the problem is the bigger you make these, the more errors you get. And so there's been this kind of conundrum, like you need to make them bigger to make them useful, but as you get them larger, then you run into more and more errors. And so researchers have been trying for a long time to figure out how to reduce those errors. And it looks like Google has developed this new quantum computer chip that really greatly reduces the rate at which the errors happen as you build computers with more of these chips. There's been a running joke in quantum computing field going back a long time that quantum computing is about 20 years away from reality. And I first encountered that joke about 25 years ago. But I think this advance and similar work by IBM and others, researchers and industry, it really does feel like that joke is out of date now and that we're a lot closer to having useful quantum computers.
Okay, so we wanted to dig into some of the science behind all of this and this question of error correction, because it really does feel like we're on the cusp of solving that problem. And you recommended that we reach out to Daniel Lidar. Tell us about Daniel.
Yeah, he is the Viterbi engineering professor at the University of Southern California. He's been a quantum computing researcher for many, many years. I first encountered him, I interviewed him and wrote about his work in the early 2000s when he was an up-and-coming researcher at the University of Toronto. He's, in addition to being an engineering professor, holds appointments in chemistry, physics, computer engineering, but his career has been really focused on developing quantum computers, and much of that in recent years has been addressing this really core problem of error correction.
Well, thank you so much for introducing him to us, Eric. We had a fascinating conversation, and thank you for that introduction.
Thank you.
When I spoke to Daniel Lidar, he told me that his interest in quantum computers began back in the 1990s.
So I got into quantum computing research shortly after a big discovery by Peter Shor, who is now at MIT. At the time, he was at AT&T Bell Labs. And he discovered an algorithm that could only run on quantum computers that could be used to solve a very hard problem in cryptography. It was to decrypt a certain type of codes that are used very broadly in internet commerce and by spy agencies and so on. That's called the RSA encryption. And I thought it was absolutely fascinating that by changing the way in which we compute from classical computers to a new type of computer, a quantum computer, we could solve a problem that seemed completely intractable, this problem of breaking encryption. But it was also very clear at the time that breaking encryption, which depending on your point of view, can be either very good or very bad for humanity. It was not the only problem that quantum computers could be very good at. There was another problem which had been theorized by Richard Feynman as one for which quantum computers could be really helpful, and that is the problem of simulating nature itself, specifically simulating quantum mechanics itself. So that was the other main reason that I got really interested, because I was actually working on problems in quantum simulation at the time, and I thought it was very cool that if we could build a quantum computer, we could simulate quantum mechanics.
Okay, time for a quick physics refresher here. Quantum mechanics is the theory of microscopic particles that are the building blocks of everything around us, from the headphones you're listening with right now to the air you're breathing. All this is made up of atoms, which contain subatomic particles like electrons, protons, and neutrons. And the way all these particles behave and interact is called quantum mechanics. How is it actually different from a classical computer?
Yes, so an ordinary computer fundamentally processes bits, classical bits. And a classical bit is just zeros and ones.
These classical bits are little packages of information of either 0 or 1 sent by transistors, microscopic switches inside the microchips in your computer.
Now, in quantum computing, we use the laws of quantum mechanics to do something that is very different. Replace a classical bit by a quantum bit, or as we like to call it, a qubit.
Qubits are the units of information used by quantum computing chips.
And a qubit can simultaneously be 0 and 1. So the or gets replaced by and. And this is very strange. Quantum mechanics allows objects to be in many states all at once. And so you put a lot of these qubits together, and all of a sudden you have a computer that can simultaneously represent many, many different possibilities. And that is the starting point for the speed up that we can get from quantum computing. And in some sense, we can actually parallel process an exponential number of possibilities for the price of one.
This ability for a qubit to be in multiple states at the same time, not just 0 or 1, is called superposition, and it's one of the key ingredients of what makes quantum computers so potentially powerful. But it's not the only one. Another is called entanglement, and this is something so strange that even Albert Einstein described it as spooky.
It boils down to there being very strong correlations between quantum particles, no matter how far apart they are. So imagine that, you and I get together and we each have a coin. And we put our respective coins in two separate boxes. And then we press a switch, each one of us on our boxes, and these coins, they flip randomly. We don't look inside the box. And one thing we do know, we know that there's a mechanism that forces these coins to land on the same side. So they're correlated, the two coins. But we don't know whether it was heads or tails. So now you enter your spaceship and you fly off to some distant galaxy.
With my coin.
With your coin, definitely, with your coin in the box. And you arrive, and at that point, I open my box and I look at my coin, and I found out that it landed on heads. Okay, so here's where the spooky thing happens. At that very instant, when I see that my coin landed on heads, your coin will also be in the state heads. And there was no force that traveled across the universe in order to enforce this correlation. It just happened. So this is the quantum correlation that we call entanglement. And this is what Einstein referred to as spooky action at a distance, because the distance could be enormous. So that seems rather spooky.
I know. It's difficult to get your head around this idea of entanglement, and physicists still don't really understand how it works, so you're not alone. But a good way to think about it is that these two coins, or particles, are entangled or linked, and the aspects of one of them depend on the other one, no matter how far apart they are. Quantum computers exploit this to drive quantum algorithms, making them very powerful.
It's actually not quite well understood yet what precisely it is about the entanglement that lets us speed up algorithms. But here's what we do know. We do know that if you take this power away, so if you just leave superposition, but you take away the power to create entanglement between qubits, then that robs quantum computing of its power altogether.
Huh. Okay.
So in other words, an insufficiently entangled quantum computer is not going to be more powerful than a classical computer.
Quantum computers haven't yet coalesced around one type of design. The qubits themselves, those packages of information being processed inside a quantum chip, can take many different forms.
So a qubit could be a photon, the elementary particle of light. Everybody knows that light can be polarized because we wear sunglasses that are polarized.
Polarized light means that the waves are manipulated to vibrate at one particular angle.
And the qubit could be a photon that can be horizontally as well as vertically polarized.
Another example is an electron. That's a subatomic particle inside an atom that carries a negative charge.
An electron has a property that we call spin. And you can think of it in some sense as if the electron can be spinning clockwise or counterclockwise. And so you can think of it as a little spinning top. And so then the qubit is the electron spinning clockwise and counterclockwise.
The third type of qubit is made from a circuit of superconducting materials with a current flowing through it.
Because it's superconducting, the current is flowing without any resistance. And now that current is flowing in a little metal loop. And again, it can have a direction, clockwise or counterclockwise. So again, you can make a qubit like that with these two directions of current flow. And that's a very popular type of qubit.
So paint a picture for me here. What do the quantum computers that are being built today actually look like?
Yeah, so if you really look inside, you will see something that is very different from the motherboard of an ordinary desktop or laptop. And the reason is that most of today's quantum computers operate at extreme conditions.
Very cold, right?
Very cold for, let's say, for these superconducting qubits. They have to be extremely cold. Or extremely high vacuum. There can't be any stray atoms flying around, possibly knocking your qubit atoms out of place. And to create those conditions, you need extreme machinery. For the extremely low temperatures, you need something called a dilution refrigerator, which is very different from the fridge in your kitchen. They get down to about, let's say, 10 millikelvin. It's much colder than the temperature in outer space.
And they also sound quite small.
The chip itself is very small, but all around this is this bulky machinery. This dilution refrigerator, for example, that's a really big device. It takes up almost a whole room. And likewise, a big vacuum pump is a big device.
So what you're describing is a kind of a very sanitized environment. I can't imagine very many people are allowed near these actual quantum computers.
If you're someone like me, a theoretician who likes to talk to experimentalists but doesn't actually do any experiments, I never go near any of these devices. Indeed, I interact with them through the cloud. Sometimes I go and visit labs, and then I get to see all the complicated electronics and so on that is there. The real experimentalists, people that are actually building the devices, of course, they do go near these devices and they tweak them and so on. But the vast majority of people who are using quantum computers nowadays, and that includes a lot of graduate students and postdocs and some professors, and also a lot of the general public who are curious and have accounts on publicly available cloud quantum computers, well, they access them through the cloud. So you're sitting at your desk and you're typing programming commands away on your laptop.
The devices currently being built by companies, governments, and university labs around the world are experiments in how to harness this quantum computational power. Remember, qubits can take different forms, and the race is on to figure out what is the best type of qubit. That's because, as Eric told us at the start of this episode, qubits are very susceptible to errors. Remember, for that quantum element of a computer to work, it needs to harness certain ingredients of quantum mechanics, including superposition, being in multiple states at once, and entanglement, that spooky behavior which made those coins flip onto the same side even when they're very far apart from each other.
Both of these properties are very fragile. We don't actually encounter these things in ordinary day-to-day life. And the reason is that actually superposition states and entangled states, they tend to what we call decohere. And this phenomenon of decoherence, you can think of it as a qubit that is in the 0 and 1 state becoming a 0 or a 1. In other words, a qubit becomes an ordinary bit. And this happens very fast. And the reasons for it are essentially the fact that there is always some kind of an external environment that is monitoring the qubit. It's as if it's looking at the qubit. Remember in the example that I gave you of the two entangled qubits or coins.
There's you and me looking at the coins.
Exactly. We were looking at the coins, and as soon as we looked, that fragile entangled state, it collapsed into, it was either heads or tails, but not heads and tails. When this happens, we get a computational error. The quantum computer is no longer performing as it should.
The speed at which this happens depends on the type of qubit. Some decohere in a billionth of a second. Others will last much longer. And by longer, Daniel says we're talking seconds or maximum a few minutes. But typically, the longer a qubit lasts without decohering, the longer it actually takes to force it to be a qubit in the first place. So there's a trade-off. The ratio between those things, how long it takes to control a qubit versus how long it takes to decohere, is called the quality factor, or Q factor.
And everybody is trying to optimize these quality factors. So let's say that you've designed a qubit that has a fantastic quality factor. Let's say 10,000. So in other words, your qubit stays alive in a superposition 10,000 times longer than it takes you to drive it into that superposition. Essentially, that means that you can apply 10,000 operations before you lose the superposition property. And so that means your algorithm can only consist of about 10,000 steps. Well, if you think about how long it actually takes to calculate something useful in real life, in many cases, it takes millions and billions and trillions of steps. And for something like trying to break public encryption schemes, it's going to take you billions of steps to do that.
So this is something that you are focusing on in your research. And I understand it's also one of kind of the things that's holding the field back, as it were, to get this right. So how do you go about fixing this problem?
Yes. So now we need to get into this area of quantum error correction. Quantum error correction is about how do I take these faulty qubits that can only last for 10,000 steps and somehow use tricks to make them compute much, much longer. And this idea of error correction, it goes back all the way to the days of vacuum tubes.
Vacuum tubes were used in the first generation of computers back in the early 20th century. These were long plastic tubes connecting different parts of huge machines.
So when people first started building computers using vacuum tubes, these vacuum tubes would explode left and right. A vacuum tube would last for probably a few minutes before you would see an explosion somewhere. So John von Neumann, who was one of the fathers of modern computing, figured out a way to deal with this problem, and this is what is called error correction. And essentially, the basic idea is to use redundancy. So instead of relying on a single bit, whether your bit is a vacuum tube or now a qubit, you use several together.
Basically, this means sending the same information multiple times. Say we're talking zeros and ones, and you wanted to send a 0. Using the concept of redundancy, you'd send your 0 10 times. Maybe 8 of them would end up as a 0 and 2 as a 1, but the majority would say 0, so you'd go with that. And when you put this idea of redundancy into practice in quantum computing, it means building devices with more qubits that are doing the work of a single qubit. How close are we to solving this problem and getting to a quantum computer that isn't just doing 10,000 algorithms before it reverts back to the same power as a classical computer?
The answer is that we don't actually have to get very much farther. So there's this very interesting thing that happens. Once you achieve a quality factor of, let's say, 1 million, and I'm saying let's say because this is another hotly disputed topic and people are working on it, but it turns out that if you achieve a certain critical quality factor, you can bootstrap a quantum computation. You can just use these faulty qubits before they crash. You can string them together using this idea of redundancy, and you can achieve a computation that can last essentially arbitrarily long. This is what is called fault tolerance.
The theory here is that by creating a code that bands together the results of multiple physical qubits into what's called a logical qubit, you can actually fix the errors faster than they occur.
And so the goal is not to make a perfect qubit that has an infinite quality factor or that has 0 error. We know that we can get away with qubits that are somewhat faulty, and then we can achieve fault tolerance, which is the ability to compute arbitrarily long with faulty components.
Last year, experiments reported by Google and a company called Quantinium suggested they got close.
They achieved what we often call break-even. Break-even is where your logical qubits, the qubits that are strung together in an error-correcting code, are better than the physical qubits that are the basic building blocks.
And then in December, Google announced with its new Willow chip that it had achieved beyond break-even.
Our logical qubits now operate below the critical quantum error correction threshold, a long sought-after goal for the quantum computing field since the theory was discovered in the 90s. And we've achieved it for the first time with Willow.
Daniel explained to me that the Google demonstration showed a string of qubits had become better than their constituent physical qubits, and even kept on improving as they scaled it up in size. That's why Google's announcement was seen as so significant. Despite all these efforts being put into error correction, Daniel says that existing quantum computers are actually able to do computations that are beyond the reach of a classical computer. This is what's known as quantum advantage or quantum supremacy.
The most famous example was, again, the Google group in 2019. They demonstrated what was called quantum supremacy, which was basically showing that with a fairly small quantum computer that they had at the time that had about 50 qubits, they were able to generate a string of random numbers that had properties that could not be reproduced by a classical computer in any reasonable amount of time.
Other groups have demonstrated examples of quantum supremacy with mathematical problems too. In his own work, Daniel has experimented with how good quantum computers are at playing a form of the game Jeopardy, where contestants are given clues to help them guess a secret word.
We essentially played the Jeopardy version with a quantum computer, and we're able to show there was a significant speed up compared to playing the classical version of Jeopardy. So this is another example of quantum advantage.
As we heard from Eric Smalley at the start of this podcast, the extra computing power promised by quantum computers could help answer some big scientific problems, whether it's finding new drugs or developing new materials. But there are also concerns about the dangers of unleashing the power of quantum computing. People have talked about security fears. So should people be scared of what these quantum computers could do as well?
Yeah, so if you can break encryption, that sounds like a very bad thing if you are the person who is trying to protect a secret. But it turns out we can use the laws of quantum mechanics to create encryption that can't be broken even by quantum computers. And this encryption is unconditionally secure. What that means is that as long as the laws of quantum mechanics are valid, then there is no way that anybody could break these codes. Okay. Whereas with something like RSA, the encryption scheme used for internet commerce, which quantum computers can break, that encryption scheme is not unconditionally secure. But quantum encryption is a different beast. It cannot be broken even by quantum computers. So it is indeed a double-sided coin, which is why in the US, the National Institute for Science and Technology has already recommended switching to quantum-resistant encryption schemes. And such schemes have been discovered and have now been recommended and are being implemented. So there is this transition period of vulnerability of encrypted information to quantum attacks, but it's going to pass. And with that in mind, I think we don't need to worry too much about the dangers posed by quantum computing. The upside in this case is really tremendous because of all these other applications with the potential to revolutionize materials discovery and drug discovery and so on. So I primarily see a huge upside.
In 2024, a number of countries in Europe, including the UK, France, Spain, and the Netherlands, moved to protect their quantum computing research. According to a report in the New Scientist magazine, they limited exports of quantum computing devices to computers of 34 or more qubits with error rates below a certain threshold, depending on the type of qubit. I asked Daniel for his views on that approach.
At that number of qubits, there is literally nothing you could do with a quantum computer that you couldn't already do quite fast with an ordinary computer. It's really going to take quantum computers having thousands of qubits and possibly millions or billions before you can really start to do damage to code breaking.
To put this into context, the most used quantum computers today have a little over 100 qubits. Google's latest quantum chip, Willow, has 105. Quantinuums are roughly around 50. But the biggest so far was launched in October 2023 by a company called Atom Computing with 1,180 qubits. And now IBM has announced its plans to release a device this year with 1,386 qubits by linking 3 new chips together.
Many countries are working independently on developing quantum computers. The biggest players are the usual suspects, the US and China, primarily, and there's also a very strong effort in Europe and in Canada and in Australia. Eventually, everybody's going to get to the finish line, I think. So in that sense, it is somewhat futile to try to prevent the spread of the technology. But you can certainly slow it down and try to gain a relative advantage if you are fearful of the security implications.
You described this kind of moment that we're at. We're almost on the threshold of something big here. But when do you expect this really to kind of take off and this error correction problem to be solved sufficiently and that we're really going to see all of what you described, all that potential be realized?
I'm reluctant to make a prediction like that. But we are at a point right now in the development of this technology where things are really going very fast. And the point is that quantum computing, for it to scale and to take off, is going to still take some real science breakthroughs, some real engineering breakthroughs, and probably overcoming some yet unforeseen surprises before we get to the point of true quantum utility. So with that caution in mind, I think it's still very fair to say that we are going to see truly functional, practical quantum computers kicking into gear, helping us solve real-life problems within the next decade or so.
Okay. Well, thank you so much, Daniel, for coming on and explaining all of this to us. It's been really great. Thank you.
It's been great fun. Thank you.
That's it for this week's episode. You can read more about breakthroughs in quantum computing on The Conversation, and we'll put links to some suggested articles to read in our show notes, including some by Daniel Lidar. This episode was written and produced by me, Gemma Ware, with assistance from Katie Flood and Mend Marawani. Sound design was by Michelle Macklem, and our theme music is by Nita Saul. Stephen Kahn is our global executive editor. You can email us directly at podcast@theconversation.com, and do reach out if you'd like to tell us what you think about the show. We'd love to hear from you. You can also sign up for The Conversation's free daily newsletter by clicking on the link in our show notes. The Conversation is a non-profit news outlet dedicated to sharing the work of academic experts with a wider audience. If you like what we do, please support us at donate.theconversation.com. And please do rate and review the podcast wherever you follow us. It really does help. Thanks for listening.